Okay, so let's proceed with a few more examples on the AC circuit analysis for MOSFET. So given the circuit here, where we can identify as a voltage divider bias circuit, and the first step is normally to do the DC analysis. Let's assume we have done that, and now we want to derive, we want to draw the AC equivalent circuit, and then we want to derive some of the AC parameters, including the input impedance ZI, output impedance Z out, and also the voltage gain, negative V out over V in. Okay. So the first step in drawing the AC equivalent circuit, I'm going to use a hybrid pi model. Okay, because there is also the T model, for example, that we are not going to cover in this class. So using the hybrid pi model that we have seen in the previous video, we're going to replace the hybrid pi model for the MOSFET, and then we'll do some analysis. Okay, so the first step is to replace all the voltage source with ground, and then to short out all our capacitors. Okay. So remember that the impact of shorting the bypass capacitor CS is that all the current will go through the wire instead of going through the RS resistor. Okay, so once we have that, now we can start to draw, and our input here we have VI. Okay, so VI we can draw something like this, and VI, and we don't have any resistor on VI, and we see that R1 is connected to ground and gate. Okay, R1 is connected to ground and gate, and R2 is also connected from gate to ground. So meaning that now we are going to have R1 and R2 both in parallel, connected to ground. Okay. And then we draw our small signal equivalent circuit. So here is our VGS. It looks something like this. Okay, and here is our GM VGS, and we see that RS is gone, so we don't have the here is our source, here is our drain, it's our gate. So our RS is gone, but we have RD is connected to the ground. So RD is connecting drain to the ground. So we can go like this. And then on V out we don't have a RL. Okay, there is no more resistor. So we just have a RD, RS, R1 and R2. Okay, but in fact here actually we're going to do something like this. Okay, we actually have the RDS. Okay, we have the RDS is connecting like this. Okay, RDS is connecting from the drain to the source, and the source is connected to ground. So here is RD, and here is actually your RDS. Okay, so let's assume RDS is not infinity, is a very large value, and there is some values to it. And our V out is actually here. So V out is the voltage across the parallel combination of RDS and RD. Okay, so this is our AC equivalent circuit with all the resistors, the current source. And what about our ZI? So ZI is here. Okay, ZI is there. The resistance seen at the input of the gate, and Z out is here. Okay, the output seen at RD towards the drain terminal. So ZI is equals to R1 parallel with R2. Okay, the total resistance seen at the gate terminal, and then Z out is just RD parallel with RDS. Okay, RD parallel with RDS seen in this part here. Okay, so if we ignore RDS, then Z out equals to RD, and then if it's a fixed bias circuit, you see in the previous video, if it's a fixed bias, then the input resistance is just maybe simply R2, or one resistor between the gate and the ground. Okay, and then what about AV? So AV is V out over V in. Okay, AV is V out over V in. So V out is we have the current going like this. So V out is actually negative GM Vgs, which is our current, multiply with RDS parallel with RD. Okay, so that's the V out. Okay, V out over V in, and V in is just here. Okay, Vgs is actually equals to V in, so here is just Vgs. So then our AV, our voltage gain, is simply cross out Vgs, so it's minus GM RDS parallel with RD. Okay, so that's derivation, and I think we can see here. Okay, so this is the model. You can see that the Zi is looking there, and the output resistance is actually looking here without the RL. Okay, without the RL and the input resistance for Zi. Okay, Z out, and so we can see here that the Zi is just a parallel combination of R1 R2, and Z out is a parallel combination of RDS or okay, so this is RD, which is RDS. Okay, we can call it RDS. Small r, okay, small r, which represents the internal resistance of the MOSFET, okay, rather than the big R there. So a parallel of RD and RDS is your output impedance, and the voltage gain, okay, as we have derived previously. Okay, so the voltage gain that we have derived, okay, which is simply minus GM RD RDS and RD in parallel. Okay, so let's look at another example here with some values. So given the circuit here, so what kind of circuit is this? Again, it looks like well, it is actually a voltage divider bias circuit. Okay, where we have the resistor R1 and R2 there, okay, in parallel. So given K, so K is given to you 0.5 milliamp per voltage squared. VGS TH is given 2 volts. Okay, this is not V Thevenin. Okay, they'll be confused with V Thevenin, VTH. So here is a threshold voltage, VGS TH, and then the RD or the RDS is infinity. Okay, which means you can ignore it in our analysis and calculation. So let's the first one is to find Vgsq and IDQ by graphical method. So this one we have already done in the previous in last week's topic on how to obtain Vgsq, IDQ using graphical method on the voltage divider bias circuit. Some other characteristics you can see, we have a bypass capacitor. Okay, we have a bypass here to see. Okay, we have a bypass. We also have a source resistance. Okay, we have a source resistance and a bypass type of voltage divider bias circuit. So if we do some analysis here, you need to find the V Thevenin, we need to find the R Thevenin. Here is given 18 volts. Okay, 18 volt given, R1 given, R2 is given. Then easily we can find our Thevenin voltage and resistance. Okay, and from the Thevenin voltage and resistance, we can do the KVL loop. Okay, we can do the KVL loop. We can get the characteristic equation, the ID equation, and all that. And finally, if we do this correctly, we should be able to get okay. So here, if you do this correctly, you should be able to get IDQ is equals to 3 milliamps, and Vgsq is equals to 4.5 volts. Okay. Okay. So IDQ we have, Vgsq we have, and now let's do number 2. Okay, so number 2. So draw the mid-band AC equivalent circuit. So what do we do first? We need to ground this one and short all our capacitor. So 2 steps there. Okay, so basically we have a V in here. Okay, V in to ground, and then we have R1 R2. We have R1 R2 going like this, and then we have VGS GM, VGS. Okay, RDS we ignore. Okay, so no need RDS. We need, if we require you to do RDS, we need one RDS there. And then so we have a bypass. So here is the source. So the RS is gone. R1, R2 is there, and then we have RD and RL. Okay, so we have, to be careful, we have both RD and RL there. So RD and RL. Okay, and our B out is across RL, so our B out is simply right there. Okay, so this is done. Number 2. Okay, so just some notation here. Our ZI is here. Okay, and our Z out is here. Okay, not including RL and not including V in. Okay, so what is the resistance seen at the input of the gate? So R1, R2 in parallel. Okay, R1, R2 in parallel, and Z out is simply RD. Okay, without the RDS. Okay, so find the impedance. We have find already. So these values are given to you. Okay, R1, R2. So ZI is just going to be 1.5 milliohms. Okay, 1.5 milliohms. And if you calculate Z out is simply 2.2 kilo ohms. Okay, which is equals to RD right here. Okay, so let's calculate AB. Let's calculate AB. So we need to calculate GM first. So remember that GM is equals to 2 square root of K IDQ. Okay, which is equals to 2 square root of K 0.5 milli times with IDQ 3 milli. And here you should get a value of 2.45 millisiemens ms. Okay, so that's our GM right there. And AB we have derived already. So AB, you have to be careful that now we have a parallel RD and RL without RDS. So then our AB is simply minus GM RD RL. Okay, so which is minus 2.45 times with RDRL in parallel. Okay, so 2.2 and 1 kilo ohms in parallel. We are going to get 0.69K. This is milli, okay, K, and eventually you should get minus 1.69 gain. It doesn't have a unit, so it's just a ratio, negative 1.69. Okay, so that's I think that's all that we need to find here. So further analysis of this. So for example, if we give a certain value on the input, because remember this one is actually V out over V in. Okay, so if we give a certain value on the input, can we calculate the output value? Okay, so for sure we can calculate if we have our AV or the voltage gain. Okay, so that's it for the MOSFET AC and DC analysis. And the next topic will cover operational amplifiers.